Alright, so today we're going to be talking about tangent and secant lines. And before we get into what tangent and secant lines are, let me just talk about the rate of change. So the average rate of change is basically defined as the change in quantity divided by the change in time, or the amount of, basically it's the same thing as doing like rise over run, right? And then this delta right here, this Greek symbol means changing. And let's just get into an example. So example, find the average rate of change of f of x is equal to x cubed minus x on the interval 1, 3. So the endpoints are 1 and 3, so f of 3 is simply 27 minus 3, that's 24, and f of 1 is 1 minus 1, which is 0, and so our average rate of change is just 24 minus 0, which is the change in quantity, over the change in time, or like the change in x, which is 3 minus 1, which is 2, and so it's 12, right? So essentially what we did out here, right, we have this sort of function, x cubed minus x, right, that was our function. If you were to factor, minus 1, so it's x times x plus 1. Those are zeros, right? Here, negative 1, 1, right? So we probably have something that looks like that, right? And we took this point at 1, and we took this point at 3, and by finding this sort of average rate of change, we're drawing a line across it, right? We're drawing a linear line across it, right? That's because what we calculated was the rise, right? The rise was just 24 minus 0, and we divided by the run, right? So 3 minus 1, and so we drew out a line across it, and that was, and 12 was the slope of that line. And this sort of line, what we did was we took 2 points and we drew a line across it, and this process of taking 2 points on a function and drawing, let me put this in quotes, because drawing a line across it is called finding the secant line. So in other words, a secant line across 2 points is basically a secant line across 2 points is the same as the finding the slope of the average rate of change across those points, and then finding the equation that describes it. Alright. Now we sort of have our intuition about what a secant line was, right? And so now we have something called a tangent line. Basically, a tangent line is the tangent line of a function is the line that represents the slope of a function at some point x. Now, to find the secant line and to find its slope is pretty easy, right? We had 2 points and we could just do rise or run, and that sort of plots out a line across it. Again, if I were to draw like, a curve like this, right? If I had point A, if I had some point B, right? I took these 2 points, I found their average rate of change, right? Because this was the rise and this was the run, right? I found its slope, and then, from your algebra class, you know how to take a slope, and like if you have a slope and a certain point on the line, which you could just take f of A or like f of B, you could find the equation, right? But how do we find out a tangent line, right? So according to definition, the tangent line is the line that represents the slope of a function at some point x, right? So if we have the same sort of graph, x, right? The tangent line will be this, the slope of this curve, or like the function at point x. So all we know is f of x, right? So how do we go about finding the slope? We don't have another point of reference to know what this value of the slope is, right? So in essence, we're doing 3 things, right? We're doing 3 things to ascertain the slope, right? And here's the 3 things. So we have 3 steps to find the tangent line. Our first one is we start off by a secant line, right? Because we know how to do that. So start with calculating slope of a secant line through this point x, and some nearby point q. Now, remember all this limit stuff that we were covering, or you should know by now, right? We find the limiting value of the secant slope as q approaches p, or sorry, x, point x. And finally, we define the slope of the curve at point P to be this number, and then this number means like the number from part 2, and basically, and the tangent line as the line through f of x with said slope. Now, this could be a bit confusing at first, but let me sort of draw it out, what these steps mean, graphically, right? So basically, let's say we had a similar function as I showed. So if our function looks like this, right? And suppose we want to find the tangent line at this point x, right? So we start off by, finding secant lines with nearby values. So we have this, so this is q. And we start bringing q closer and closer to x, right? So we have, maybe this is q2. And so that will be the new secant line. Now this is q3. That will be a new secant line. It's getting, you know what, let me use a different color. Alright, so let's say this is Q, so that'll be our secant line. Now we bring Q closer to X, so this is Q2. We have a new secant line that looks like this, Q3, and we see how it's almost looking like the tangent line. And finally, when Q basically becomes X, right, when we bring Q to X, so that's the limiting value, we'll have some line that looks like this. And we see how it's tangent to the curve, and it becomes the tangent line. So now this is the tangent line. So see how as we kept bringing Q closer and closer to X, we approached the tangent line. Now how do we do this algebraically? Well, it's pretty simple, right? So you have a so I'm going to give you a definition of how to do this algebraically. So slope of a curve at a point is, so slope of a curve, y is equal to f of x at a point p of a comma f of a is m is equal to limit as h tends to 0 f of a plus h minus f of a divided by h. Now take a moment to sort of understand what this limiting function is doing. You can see how it's basically doing those 3 steps that I described in the previous slide of how to take a secant line and converge it towards a tangent line, right? So basically f of a plus h, right, is this point Q right here. We're taking some distance away, right, h, and we're subtracting it from a, right, and our delta, our run, is h, right? So this is basically finding the average rate of change, right, our secant line. How to find the slope of the secant line. We take 2 points, and we find their difference, and we divide it by the distance of those 2 lines, right? Because h was the distance, and this is 0.1, and this is 0.2, right? And what we're doing is we're bringing this delta closer and closer to 0. That's what we're doing with the limit. And we saw graphically how this same thing leads to the secant line, the tangent line, because we take the limit to a 0, and that's when we're converging this point Q to X, right? And by doing that, we get the slope of the tangent line, because our slope basically is at the same point itself. So let's do an example. And basically, we get the slope of the tangent line through this, and then we can find the tangent line itself by using stuff we learned from algebra of how to find the equation of the line given the slope and a point on the line, right? And the point on the line would just be like f of x. We know x and we know f of x. Alright, let's look at an example. Alright, I'll just do an example. F of x is equal to 1 over x. Find the slope of the curve at point A. So slope at x is equal to a, right? So this is just plugging in. Limit as h tends to 0, f of a plus h minus f of a divided by h, which is equal to limit as h tends to 0, f of a plus h is x plus, a plus h, 1 over a plus h, minus 1 over a, divided by h. Now we just use like our limit techniques of how to solve limit problems. One thing we could do is, group these together. So we get a minus a plus h divided by a times a plus h over h. Ooh, I'm running out of space. Let me just bring this over here. So that brings us minus h over h times a plus h. These two cancel out, so this is just equal to minus 1 over a times a plus h. And remember, it is limit as h tends to 0 of this. And so our final answer is just minus 1 over a squared, right? Because this term right here, a plus h, is just going to become a because h is going to 0. Alright. Alright, so from part A, we knew that the slope at x equals a for f of x is equal to 1 over x is minus 1 over a squared, right? We just did that in the previous part. So given this, where does m equal negative 1/4? And m is the slope, right? So it's just a plug-in problem. Minus 1 over a squared is equal to minus 1 over 4, right? We get 4 is equal to a squared, right? And then, so a is equal to plus or minus 2. Remember, when you take the square root of this, it could either be plus or minus 2 because it's a squared, right? So either at a is equal to 2 or negative 2, our slope is going to be negative 1/4. Alright, this is a pretty good exercise. Now let's talk about our final part for today, is finding the normal line. Alright, so what is the normal line? So normal line is the line that is perpendicular to the tangent line. So graphically, if you have this sort of function, this is our tangent line. Let me do a different color. If this is our tangent line, then our normal line will look like this, right? Because it's perpendicular. How do we go about doing this? Well, it's pretty easy. Recall that if a line with slope m is perpendicular to another line, the other line has slope minus 1 over m. Basically, when two lines are perpendicular, their slopes are negative reciprocals of each other. And this concept is going to help us find out the normal line, right? So this process is pretty easy. We know how to find the tangent line of a given function, right? So we find the slope of the tangent line, and then we just find the negative reciprocal, and that's the slope of the normal line. And to find the normal line that goes to that point, we just use, again, we use algebra concepts, and we know the slope of that normal line. We know the point, we find the equation line going through it. So let's do an example. Find the equation for the normal line through f of x is equal to 4 minus x squared at x equals 1. So let's find the slope of the tangent line as x equals 1, and that's just limited as h tends to 0, f of, and in this case h is, a is 1, right? So 1 plus h minus f of 1 divided by h, which is equal to limit as h tends to 0, 4 minus x, or 1 plus h whole square minus 4 minus 1 whole square divided by h, which is equal to limit as h tends to 0, 4 minus 1 plus 2h plus h squared minus 3 over h equal to limit as h tends to 0, 3 minus 3, so that cancels out, minus 2h minus h squared over h, which is equal to just limit as h tends to 0, minus 2 minus h, and h goes to 0, so this is equal to minus 2. So we know the negative reciprocal of minus 2 is just 1/2, right? So that is m of our normal line. And we know f of 1 is equal to 3. So basically, we're just finding out the equation of a line with slope 1/2 that goes to this point. And now we just use algebra to find this out. So y minus 3 is equal to 1/2 times x minus 1, and that's just y is equal to 1/2 x minus 1/2 plus 3, so y is equal to 1/2 x plus 5 over 2. Easy. And that is the slope of a normal line through x equals 1. Yeah, and that is basically it. We'll see in the future, or you might already know, that this process of this finding the tangent line is basically like finding the derivative, and then plugging in the point, because the derivative is going to give you a general equation for the slope of a line, and you plug it in at the specific point, and that basically allows us to find the tangent lines at this point. So you'll also notice that later on, this practice of finding the tangent line is finding the instantaneous change, rate of change at a point. So physics has a lot of applications, like the instantaneous rate of change of position with respect to time is like the instantaneous velocity of the speed of something. And we'll see later on how derivatives are important, and finding this tangent or the normal is pretty important.